Okay, so today we will finish off one last remaining section from chapter 3, which is about rational functions, and then we will go to section 4.2, so that is in chapter 4, which is the calculator heavy sections for 4.2 through 4.5. Okay, so this is not a calculator section, 3.5. This is just pure non-calculator section. Anyways, so rational function. So in chapter 1, I believe, we saw rational equations, okay? So the rational function is defined in a similar manner. So basically, the word rational means fractional, okay? So the rational functions have the form p of x over q of x, okay? So here, we saw q of x in section 3.2 when we did the synthetic division, okay? And q of x was the quotient. But here, there's no synthetic division. It's just p of x and q of x are just polynomials. Okay, so these are just polynomials. Okay, so that's what rational function means. So rational function has two polynomials that are formed a fraction, okay, like in a fraction. So there's a polynomial at the top and there's another polynomial at the bottom, okay? Now, the most basic rational function is 1 over x, okay? So this is the most basic rational function, and we have seen its graph before, okay? And hopefully you still remember how the graph looks like. So first of all, none of you has to say the graph is a line, okay? That's just absurd, right? Okay, so the graph is not a line. So the graph has two curves, okay? And so where is one curve? So where is one of them? It's in the first quadrant, and hopefully you remember how the curve looks like. Something like this. Okay, so by looking at this curve, it should remind you where the other curve is. Okay, it's in the opposite spot, right? Which is where? In the third quadrant, right? Like that. Okay, now, what is the domain of this 1 over x? So the domain, remember, means what? The x values, right? Okay, and since this is a rational function, we have to always think about what? The so-called bad values, okay? The values of x that make the fraction undefined. And is there any such x values?
0.
0, right? Yeah, so what does that mean? The domain is everything but 0, right? Okay, so basically you said, you know, the denominator equal to 0, but actually it can't be equal to 0, right? Okay, so what's the domain? Negative infinity, comma, 0, union, 0 to infinity, right? Okay, and now the range. Okay, so remember the range is the y values, right? Now, by just looking at the graph, what seems to be the range?
Everything but 0.
Everything but 0, yes. Okay. So the range is the same thing as the domain. Okay. So now, let's look at problem number 2. So number 2 is 1 over x plus 2. Okay. So now, how can we get its graph? So, so for this one, let's try to use 1 over x, okay? So now, what's the difference between 1 over x right here, and 1 over x plus 2. You add 2 to x, right? Okay, now does it remind you anything that we have seen, let's see, for this past exam? So this is f of x plus 2, where f of x is 1 over x. Okay, so you are adding 2, or you are adding something to x. So that means a shift. Now, what kind of shift is it?
Horizontal.
The horizontal, okay. Now, left or right?
Left.
Left, right? Yeah, remember that? Because when we add something to x, it seems we have to go to the right, but we always have to think backwards for the horizontal case, right? So this means move 1 over x left 2. Okay, so now what do you expect to happen in terms of the graph? So if we look at this graph, so there's this like big blow up part here, okay, and then there's this big like falling down part, okay. So what do you want to happen? So basically it will maintain these two curves, right? Okay, but then what is changed? This like big separation line here, which is the y-axis in this case, we're gonna be somewhere here, right? Because you have to push this entire graph to the left. Okay, so it looks something like something like this, right? Okay, so now there's this kind of like invisible separating line in the middle of these two curves, okay, which is no longer the y-axis, right? Because we have been shifted to the left side by 2. Okay. Okay, so now what is the domain of this function?
Everything but -2.
Everything but -2, yes. Do you see why? Okay, you set bottom equal to 0, so you get x is equal to -2, which means x can't be equal to -2, right? So here the domain is not everything but 0, unlike the previous problem, okay, but it's everything but -2. Now, is the range same thing as before? Everything but 0. Yes, right? Because here all the positive y values lie on the top curve and all the negative y values lie on the bottom curve. Okay, so the range stays the same. Okay, so now let's revisit these two graphs. Okay, so let's go back to the first graph here. Okay, so now look at these two portions. Do you think the graphs touch the x-axis at these two portions? No, okay. Now let's look at these two portions. Do you think the graphs touch the y-axis? No, okay. But the thing is, all of these 4 portions, so on these 4 portions, the graphs get really closer to the corresponding axis, but they don't actually touch. Okay, so we can say no touch, no touch. Kind of bizarre expression, but I guess it makes sense. Okay, like no touch. Okay, and now by looking at the bottom curve, so again, do you see the 4 specific regions where the similar phenomenon is observed? Okay, and where are they? Here, 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 and here, right? Okay, and the thing is, if you look at this portion like really closely, you'll see that there's like very tiny gap in between my curve and the x-axis, so I didn't violate that rule. So here, again, the same thing happens. Okay, so the graphs do not touch the x-axis or this dotted line. even though it seems like they do touch. Okay, so again, you can see that some portions of the graphs, either here or here, they blow up. Okay, so where do they blow up? Here, right? And some portion falls down right here. Okay, and what about these two? So these two do not blow up or fall down, right? Rather, they more kind of look like the horizontal line, but it's not a horizontal line, right? Okay, and same thing right here. The graph blows up here, it falls down here, but then the graphs start to resemble the horizontal line at these two portions. Okay, so is there a name? Is there a name to denote these phenomenon or phenomena? And the answer is yes. Okay, so again, like I've mentioned all of these here, like either blowing up or falling down or becoming flat. Okay, so here are their names. Okay, so first, blowing up or falling down, that is part of the vertical asymptote. Okay, and for the abbreviation, which is adopted by me actually, I always use the word VA for the vertical asymptote. Okay, so the vertical asymptote is a vertical line such that the graph either blows up or falls down. Okay, so the graph has to blow up or fall down for the vertical asymptote. Okay, now here actually, like, there's a small aligning issue, which is this. So the general form of the vertical asymptote is this: x equals some number. Okay, and hopefully you can see why. Because whenever you see x equals some number, that's the equation of what? Any vertical line, right? And it makes sense because vertical asymptote is a vertical line. So it has x equals some number. Okay, so there's no y. Okay, and now the second asymptote, horizontal asymptote. And the abbreviation that I use is HA. Okay, so now what does that mean? First of all, it's a horizontal line such that the graph, and now this time, the graph does not blow up or fall down. Okay, rather, the graph starts to flatten out, okay, which means it kind of resembles the horizontal line. Okay. And now, what is the general form of any horizontal asymptote? So for that, we have to think about what's the general form of any horizontal line, and that means y equals some number. Remember that? Okay. And now, these two are the two popular asymptotes, but there is another one that is less popular than the other two, but still it is important. And it's called oblique asymptote. Okay, and its abbreviation is OA. Okay, so in short, you can say like Baha-Wa. Kind of sounds like an alien language, but it's like Baha-Wa. Anyways, okay, it's Monday, so you know, like things can be crazy. Anyways, so oblique asymptote. So we have covered the vertical line, the vertical asymptote, and the horizontal line, horizontal asymptote. So what is the oblique asymptote? So somewhere in the middle of the vertical and horizontal line, which is what? The diagonal line, right? Okay, so this one is a diagonal line or slanted line such that, okay, so now it's in the middle of vertical asymptote and the horizontal asymptote. So what do you expect to happen? It has all three phenomenons, okay, such that the graph blows up, falls down, or flattens out. Okay, so it observes all three phenomena given, so there's an extra condition, given that the graph gets closer to this OA. Okay, so you'll see why I have added this extra condition. Okay, so as long as the graph gets closer and closer to some diagonal line, and if the graph starts to blow up, fall down, or flatten out, then it is an OA. Otherwise, it's not. Okay, and you will see that in the previous two examples. Okay, so now, what is the general form of this oblique asymptote? Maybe you can take a guess. Okay, so it's not a vertical line, it's not a horizontal line, it is a diagonal line. And what was the general form of any diagonal line? So maybe think of something like this.
Mx plus b.
Y equals mx plus b, yes. Which is what? The slope-intercept form, right? Okay, so it's the equation of any general line. Okay, so that has to be the equation for the OA. Okay, so now let's go back to the previous two examples and let's find the asymptotes. Okay, so example number one. So that was 1 over x, right? So go back to the page before. Is there any vertical asymptote, which means is there any vertical line such that the graph blows up or falls down? Yeah, right, which is what? This one, right? Okay, now this is the y-axis and that's obvious, right? But remember, any vertical asymptote has the form x equals some number. So the question is, what should this number be for the y-axis?
0.
0, yes. Okay, so the vertical asymptote is x equal to 0. Okay, which is same as the y-axis. Yes, that is true, but you shouldn't say y-axis. You must say x equal to 0 because we have to follow the specific form x equals some number. Okay, and now, is there any horizontal asymptote? Okay, so the horizontal asymptote means what? The graph kind of looks like a horizontal line, right? So do we have any horizontal line, such horizontal line? Yeah, it's this one, right? Which is what? The x-axis, right? Okay, but just like the vertical asymptote, the horizontal asymptote has the specific form, y equals some number, right? Okay, so the question is, what should this number be for the x-axis? Y equals what?
0.
0 once again, right? Yes. Okay, and just like the vertical asymptote, you shouldn't say x-axis is the horizontal asymptote. You have to say y equal to 0. And now, is there any oblique asymptote for 1 over x? So the thing is, most people say that is the oblique asymptote because the graph is blowing up from this. But is this the oblique asymptote? And the answer is no. And why not? Even though the graph is blowing up, what's the problem? Is the graph getting closer to the graph or is it moving away from the graph? It's moving away from it, right? Like that. Okay, and same thing for this portion, right? Okay, so the graph never gets closer to this line. So what does that mean? There's no oblique asymptote. Okay, that's not the oblique asymptote because, I mean, the graph is once again blowing up, but it's moving away from it. Okay, so for the OA, there isn't one. Okay, so now let's look at the second graph, which was 1 over x plus 2. Is there any vertical asymptote? Yes, which is what? This dotted line, right? Okay, so now it has to have the form x equals some number, but what should that number be?
-2.
-2, yes. Okay, so that point is -2. Okay, and now do we have any horizontal asymptote? Yes, it's same thing as before, right? Y equal to 0. Does it have oblique asymptote? No. Once again, that's not the oblique asymptote, right? Because the graph is moving away from this. Okay, so there's no oblique asymptote. So again, going back to here, the vertical asymptote, x equals -2. Horizontal, y equal to 0. Oblique, none. Okay. Okay, so any questions over these basic asymptotes? Okay, so now, by just looking at the graph, it's not hard to figure out the asymptotes, but can we get them algebraically? And the answer is yes. Okay, so here's the scheme to find each asymptote. So here is the critical condition. Suppose our rational function p of x over q of x has no common factors. Now, what does that mean, having no common factors? If you can factor top and or the bottom, okay, so here I said when, but I guess I have to say if. Okay, so if possible, when you factor top and or bottom completely, I guess grammar mistake, but it's not a big issue in math, okay, nothing is in common. Okay, so that's what I mean by that, having no common factors. Okay, now, people sometimes ask, well, what if there are common factors? Oh, you'll see, okay, in about 2 pages from now, okay? But for now, we have to assume that there's no common factors. Now, the vertical asymptote, the scheme is set bottom equal to 0 and solve. Okay, so that's the scheme of finding the vertical asymptote. And now, have we seen this scheme before? Set bottom equal to 0 and solve. Yes, and where did we see it? Finding the bad values, right? Okay, when we are finding the domain of rational functions, that's what we do, right? Okay, yeah. Okay, so it's the exact same thing. Okay, so same as finding bad values. Okay, but of course we are not finding the domain here, so we can just stop there. Now, the horizontal asymptote. The common misunderstanding that people make is, oh, so now we set top equal to 0 and solve. Okay, so for the horizontal asymptote, we look at the degrees. Remember, the degree means what? The largest exponent, right? Okay, so suppose the P of x, which is the top one, has degree n, and the bottom one, Q of x, has degree m. Okay, now there are 4 cases. Actually, there are 3 cases, but the last case can be split into the 2 sub-cases. But case number 1, n is less than m. Okay, so now what does that mean? So this is really sloppy representation, but bigger bottom. And hopefully you can see why. Because here this one says what? The bottom degree is bigger, right? Okay. So to put things in a simpler way, you can always remember, oh, bigger bottom. Then the horizontal asymptote is y is equal to 0. Okay. And please be careful to include y equals in front. If you just say 0, then guess what minus plus will say? Your answer is wrong. Okay, so you must specify what is equal to 0 in front. Okay, so that's the horizontal asymptote. And now case number 2, n is equal to m, which is on the next page. Okay, so n is equal to m. Okay, so now what does that mean? Top is equal to the bottom, right? Okay, again, I'm being really sloppy here. That's actually false, right? Because our rational functions will have different denominator and numerator, but top degree is equal to the bottom degree. In this case, we look at the leading coefficients. Okay, so the horizontal asymptote has the form y equals the leading coefficient of the top divided by leading coefficient of the bottom. Okay, so basically the top leading coefficient will stay at the top, bottom leading coefficient will stay at the bottom. Okay, and now the third case is apparently what? The top is bigger, right? Okay, and that's where we have 2 subcases. So now top is bigger and it's bigger by 1. Okay, so I always say bigger top by 1. Okay, so now what does that mean? Bigger top by 1. For example, the top degree is 3 and the bottom degree is 2. So apparently the top degree is bigger, but it's only bigger by 1. Okay, not any other number. In this case, there is no horizontal asymptote. And this is the only case where the oblique asymptote exists. And now, the question is what? How do we find the oblique asymptote? So, to find the oblique asymptote, you have to follow certain scheme. So, step number 1, divide the top by the bottom using the synthetic division. using the synthetic division. Okay. And then step number 2. So earlier in section 3.2 or 3.3, we mostly have looked at the remainder for the synthetic division. But for now, we do not look at the remainder. We only look at the quotient. Okay. So you just write your answer as y equals, okay, remember the equation of oblique asymptote is y equals mx plus b. But instead of mx plus b, you have to look at the quotient. Okay, so whatever quotient you get, put y in front, or y equals in front. Okay, so this is kind of like sloppy notation, but whatever quotient you get, you put y equals in front. Okay, so it's not like y equals just quotient, like the word quotient. Okay, so it's y equals whatever quotient that you get. Okay, so we don't ever look at the remainder here. And the last case, bigger top by more than 1. Okay, so what does that mean? The top degree is, say, 4, and the bottom degree is 2. Okay, then the top degree is bigger by 2, which is more than 1. In this case, there's no horizontal asymptote either, and there is no oblique asymptote as well. Okay, so I didn't write the oblique asymptote for the other cases, but like I said a few minutes ago, that is the only case where the oblique asymptote exists. For every other cases, there's no OA. Okay, so no OA for case number 2, and no OA for case number 1 as well. Okay, so basically horizontal asymptote and oblique asymptote are kind of related in the sense that you can get oblique asymptote given the conditions satisfied for the horizontal asymptote. Okay, so the oblique asymptote, remember, only exists when the top degree is bigger by 1. For every other cases, there is no slanted asymptote. Okay, so let's apply these schemes to the problems. So find the asymptotes for each of the following rational functions. Okay, so we have 4x minus 2 over x plus 1. Okay, now, before you find any asymptotes, you always have to check for what? Top and bottom have no common factors. And what does that mean? If or when you factor top and bottom, there's nothing in common. Okay, so how do you check it for this rational function? Let's see if we can factor top and bottom. Okay, so 4x minus 2. So that is possible to factor, right? Okay, because you can take out what? 2, right? Which is the GCF. Okay, now the bottom, x plus 1. Can you factor that? No, right? Because x plus 1 has the GCF 1, right? Okay, so x plus 1, you can't. Okay, so what does that mean? We have 2 times 2x minus 1 all over x plus 1, right? And now, is there any common factor between top and bottom? No, right? Because we have 2 or 2x minus 1 for the top, but at the bottom we just have x plus 1, right? So there's no common factor. Okay, so nothing in common. Okay, so now once you check that, it's easier or the easiest to find the vertical asymptote first, because remember, what's the scheme? You set bottom equal to 0 and solve, right? Okay, so what does that mean? X plus 1 is equal to 0. And so what do you get? X is equal to -1, right? Okay, now that's the bad value, but remember, we are not finding the domain or bad values, right? And if you look this closely, x equals some number. That's the equation of any vertical line, right? So what does that mean? That's it. Ooh, how simple is that? Okay, but again, of course, we have to go over some screening process at the beginning, but still, that's it. Okay, and just like the horizontal asymptote case, make sure to include x equals in front. Okay, if you don't write x equals in front, MLP will say your answer is wrong. Okay, so always write the variable in front. Okay, and now horizontal asymptote. Okay, so again, we are not setting top equal to 0, right? We look at what? The degrees, right? Okay, so look at the degrees. Now, what is the top degree? And what is the bottom degree?
Both 1.
Both 1. Do you see that? Because the degrees mean what? The exponents, right? So the exponents for top and bottom are both 1, right? Okay, so what do you notice here? Oh, they are the same. Okay, so that means what? We have to look at what case? Case number 2, right? Case number 2, top degree is equal to the bottom degree. Okay, so what do we now have to find? The leading coefficients for top and bottom, right? Okay, so now what is the leading coefficient of the top? And what's the leading coefficient of the bottom?
2 and 1.
2 and 1? Oh, not 2.
4.
4, yes. Do you see why? Because remember, the leading coefficient belongs to the degree term, right? Okay, and what's the degree term? It's this one and this one, right? Okay, so it's 4 and 1. Okay, so now 4 over 1, that could be reduced, right? So what is the horizontal asymptote? Y equals to 4. Okay, so if you can reduce any fraction, you must. Okay, and now oblique. So where is the oblique asymptote? So according to scheme number 2, what does it say in terms of the oblique asymptote? There isn't one, right? Okay, because remember, the oblique asymptote exists only when the top degree is bigger by 1. Okay, for every other cases, there isn't one. Okay, so none. Okay, so now part B. 2x minus 5 over x squared minus x minus 6. Okay, so again, let's factor top and bottom to see if there is any common factor. So first, 2x minus 5. Can this be factored? No, right? Because there's no GCF, right? Oops, can't. Now, what about x squared minus x minus 6? Can that be factored? Yeah. What times what? So what are the two factors here?
X minus 3 and X plus 2.
X minus 3 and X plus 2, right? Yes. Okay, so what do you have? You have 2x minus 5 over x minus 3x plus 2, and it's obvious that there's no common factor, right? Okay, so nothing in common. Okay, nothing in common based on this. Okay, so now the vertical asymptote. So that means we set bottom equal to 0, right? Okay, so what does that mean? X minus 3 times x plus 2 equals 0. So what do you get from here? X is equal to 3 and what? -2, right? Okay, so now how many vertical asymptotes did we get? 2, right? Okay, so in part A we only got 1, but here we got 2. Is it normal? Oh yeah. Yeah, sometimes for like extremely hard rational functions, you can have like 1,000 vertical asymptotes. Yeah, I'm not joking. Like that also happens. But just keep in mind, one vertical asymptote is not the only case. You may see multiples, okay? And horizontal. Okay, so remember you look at the degrees for the horizontal asymptote. What is the top degree and what is the bottom degree? What is the top degree?
1,
And what's the bottom degree?
2.
2, right? Yeah, because those are the largest exponent. Okay, so now what is bigger? Oh, the bottom is bigger. Okay, so bigger bottom. So that means what? Case number 1, right? So what does it say? Bigger bottom, so y equals to 0, right? Okay, and what is the oblique asymptote? None. Do you see why? Because remember, oblique asymptote only exists when top degree is greater by 1, right? For every other cases, there isn't one. Okay? Okay, so now, next page. X squared plus x over x minus 1. Okay, so again, let's see if there's any common factors. So, can you factor the top, x squared plus x? Is it possible? Yeah. What's the GCF? X, right? Okay, so it's x times what? X plus 1, right? And now, can you factor the bottom, x minus 1? No, right? Okay, so you have x times x plus 1 all over x minus 1. So is there any common factor? No. Okay, now x is not the common factor, right? Because the bottom x is not multiplied. Okay, so nothing in common, right? Nothing in common. Okay, so now vertical asymptote. So that means set bottom equal to 0. So x minus 1 is equal to 0, so x is equal to 1, right? Okay? And now, horizontal asymptote. So we have to look at the degrees. What is the top degree? And what is the bottom degree?
Two and one.
2 and 1, right? Yes. Okay, so apparently top is bigger. Okay, so what does that mean? We have to look at case number 3 or 4, right? So for the horizontal asymptote, there isn't one. Now, is the top degree bigger by 1? Yes, right? So what does that mean? There will be the oblique asymptote. Okay, so there will be the oblique asymptote. So now, how do you find oblique asymptote? You do the synthetic division, right? And it says you divide top by the bottom. And for the synthetic division, remember, you need the dividend and the divisor. Which one is the dividend? X squared plus x or x minus 1?
The top one.
The top one, right? Yes. Okay, so that's the dividend. And that's the divisor, right? Okay, now for the dividend, what do? You take coefficients, remember that? Okay, so what are the coefficients? 1 for x squared and 1 for x. Now, is there any missing coefficient here? Yes, which is what? The number term, right? So we have to put a 0 there. And now, what do you write outside?
1.
1, right? Yeah, remember that you put divisor equal to 0 and solve, right? So you write 1 outside. Okay, so now do the division. What do you get? 1, 1, 2, 2, 2, right? Okay, so now apparently the last 2 is the remainder, which we don't even look at it, right? Okay, so what's the quotient here? The quotient is x plus 2, right? Okay, so the quotient is x plus 2. So what's the answer? Y is equal to x plus 2. That's the equation of the oblique asymptote. Okay. And as you can see, this is what? This is a diagonal line, right? Which is an increasing line that looks like this. Okay, so it's the slanted line. Okay, so now the last problem, f of x equals 2x over x squared plus 1. Okay, so now let's try to look for the common factors. Can you factor the top 2x? No, right? Can you factor the bottom, x squared plus 1? Is it x plus 1 quantity squared? No, right? Yeah, be careful. So you cannot factor top or bottom. So what does that mean? Nothing is in common. Okay, nothing is in common. So the vertical asymptote, you set bottom equal to 0, x squared plus 1 equals 0. And now we have seen similar equations like this before. What do you do next? Minus 1. And then to isolate x, what do you do? Square root, right? So what is this? X is equal to square root of -1, right? Right?
Plus or minus the square root.
Plus minus, yes. And what is square root of -1?
Wouldn't it be 1?
1? What is square root of -1? That's not a real number, right? I, yes. So plus minus I. So now here's my question. How many vertical asymptotes did we get?
None.
Oh, none. Why?
Because those aren't real numbers.
Do you see why? Okay. So now, where are any asymptotes? So any asymptotes exist on where? X, Y plane, right? Okay. And now on any XY plane, where is I? Nowhere, right? Okay. So yes, this is an imaginary number. And in that case, there is no vertical asymptote. Okay, remember any asymptotes exist on XY plane where there is no I. Okay, so whenever you get some kind of I, that means there is no corresponding asymptote. And now, horizontal. Okay, so now what is the top degree? And what is the bottom degree?
One and two.
1 and 2, yes. Okay, so what is greater? The bottom is greater, right? So what does that mean? Due to case number 1, y is equal to 0 is the horizontal asymptote. And oblique. Does oblique asymptote exist? No, right? So none. Okay. Okay, so in these problems, as we saw, the top and bottom had no common factors. But what if there is a common factor? So here's an example. So suppose your f of x looks like maybe something like this. Okay, so then there is a common factor, right? Which is x minus 2. So what do you do here? Just cancel them, right? Okay, and you just have what? X plus 2 over 1, which is equal to x plus 2, right? Okay, so if there is a common factor, we can cancel it. Okay, and now, moreover, there will be an empty hole at the 0 of the common factor. Okay, so now what does empty hole mean? This one. Okay, that's not a 0. Empty hole. Okay, so a point is missing basically on the graph for the 0 of the common factor. Now here, be careful, it's not a number 0, right? It's the word 0. Okay, so going back to this specific example here, what does that mean? There will be an empty hole at x is equal to 2. Why? Because the canceled common factor was x minus 2, and to get a 0, you set it equal to 0, right? So there will be an empty hole at x is equal to 2. Okay, and this means no asymptote. No asymptote at such canceled common factor. We just have an empty hole. So now we have to be very careful with finding the asymptotes. So before you find any asymptotes, what do you have to do? Which is what we did in the previous 4 problems, factor top and bottom. And why do we do that? Because we have to look for the common factors. Okay, and look for the common factors. Now, if there is one, what do you have to do? Just cancel it. Okay, and now, this is the weird scheme, the only basically weird scheme. To find the vertical asymptote, what do? You set bottom equal to 0, right? But what kind of bottom are you setting equal to 0? Set new bottom equal to 0 and solve. Okay, why did I say new bottom instead of just bottom? Because going back to this example here, x minus 2 was the original bottom, the original denominator, but what is the new denominator? 1, right? Okay, so you said 1 is equal to 0, but look at this, that doesn't make sense, right? Because that's just a false statement. Okay, so there is no vertical asymptote here. Okay, it's not at x is equal to 2 because that's where the empty hole is. Okay, and for the other 2 asymptotes, you can use the exact same scheme as before. Okay, so the only scheme that's a little bit different is the vertical asymptote. Okay, so now let's illustrate all of these for the following 2 problems. Okay, so again, it's same thing as before, find the asymptotes. And now you will see why you have to be careful with the common factors. So x squared minus 9 over x minus 3. Now, can you factor the top? Yes, what times what? So the top is what? The difference of squares, right? So what does that mean? X plus 3, x minus 3, right? And can you factor the bottom? No, right? So x minus 3 stays the same. And now, is there any common factor? Yes, right? Which is x minus 3. So you just cancel them. And you are left with what? X plus 3 over 1, which is equal to x plus 3, right? Okay, so now, vertical asymptote. So what do? You set the new bottom equal to 0, right? And what's the new bottom? 1, right? Okay, so you said 1 is equal to 0. What does that mean? Where is the vertical asymptote? At x equals 1? No, this is false, right? So what does that mean? There is no vertical asymptote. Okay, but instead, what do you have at x is equal to 3? You have an empty hole, right? Okay, but at x is equal to 3, there is an empty hole. Okay, there's no asymptote there, you only have an empty hole. And now, horizontal asymptote. So what do you do here? Look at the degrees, right? Okay, so what is the top and bottom degrees? So for the top degree, you can say either 2 or 1. Now, if you say 2, you are looking at the original function, right? But some people choose to say 1, and hopefully you can see why. They are looking at this new function. Okay, it doesn't matter. Now, for the bottom degree, so what's the bottom degree? So if you look at the original function, the bottom degree is 1, right? But if you look at this new function, which is just 1 as the denominator, what's the degree? 0, right? Okay, so no matter which function you are looking at, what do you observe? The top degree is bigger by 1, right? So what does that mean? First of all, there's no horizontal asymptote, but is there any oblique asymptote? Yes. So where is the oblique asymptote? Now, remember, it has the equation y equals mx plus b, right? And we have to do the synthetic division, but before we do that, can you even guess the equation of oblique asymptote? Hint, we already got the equation somewhere in this work. We already got it.
X plus 3.
X plus 3, yes. And where did we get it? This one, right? Okay. So, if you want, you can verify it. So, do the synthetic division if you want. So, what do? You take the coefficient of the top, which is the dividend. So, what do you get? 1, 0, negative 9, right? And then the divisor, which is equal to x minus 3. So, you write 3 in front, right? So, what do? 1, and then 3, 3, 9, and 0, right? That's the remainder, which we don't even look at it. That's the quotient. Is that equal to x plus 3? Yeah. Okay. But x plus 3 was the result of the reduction of this fraction. So that is the equation of the oblique asymptote. Okay. And now, part B. X minus 2 over 2x squared minus 5x plus 2. Okay, so now let's factor top and bottom. Okay, so now I'm not gonna write this, but you can easily see x minus 2 cannot be factored, right? So in order to factor this function, what do you really have to factor? Only the bottom, right? 2x squared minus 5x plus 2. Can that be factored? It should, right? Yeah. Okay, so what do you get? So the two numbers are what? Negative 1 and negative 4, right? Okay, so you get like what? 2x squared minus 4x minus x plus 2. So that, right? Okay, so what do you get? 2x minus 1 and x minus 2, right? Okay, so you have x minus 2 over 2x minus 1 times x minus 2. Is there any common factor? Yeah, x minus 2, right? So cancel it. And what do you have now? 1 over 2x minus 1, right? Okay, so now how do you find the vertical asymptote? You set the bottom equal to 0, but now what is the new bottom? 2x minus 1 only, right? Okay, you don't set x minus 2 equal to 0 because it's gone, right? So what do you get here? X is equal to 1/2, right? Okay, so that is the only vertical asymptote. And remember, at x is equal to 2, there is an empty hole. Okay, there's no asymptote there. And now, horizontal asymptote. So here you look at the degrees. Okay, so what is the top degree? Maybe you can say 1, but if you look at this new function 1 over 2x minus 1, you can say the top degree is equal to 0. Okay, and what is the bottom degree? The bottom degree, maybe you can say 2, but if you look at this new function 1 over 2x minus 1, you will say the bottom degree is 1. But no matter what you are looking at, what do you notice? The bottom degree is bigger, right? Okay, so what does it mean? The horizontal asymptote is y is equal to 0. Okay, and now oblique. Is there any oblique asymptote? No. Okay, so oblique asymptote, there isn't one. Okay, any questions up to this point? Okay, so once again, first of all, finding asymptotes requires you to remember all the schemes. And number 2, you have to check for the common factors between top and bottom. Okay, if there is one, there won't be any asymptotes there. Okay, so now the last thing that we will do in the section is graphing a rational function. Okay, so now graphing rational functions can be scary, but we can have a few ingredients which will make us or make our lives a little bit easier. So first, we will find all of the asymptotes. And then number 2, we will find a few points. The 2 of the points are fairly easy to find, x-intercept and y-intercept. And then we plug in a few small whole numbers to x to come up with several other points. Okay, so now the good news is, I think if I remember right, which is I think 99.9% correct, all of the graphing rational functions in your homework are about multiple choices. There's no like physical graphing, okay? So as long as you can get these asymptotes and get the x and y intercepts and then get a few points, you can just like look at a few options and choose the right answer. And if I remember right, which is also 99.9% sure, that will be the case if these graphing rational functions appears on exam 4. Okay, so there we go. I'm just like revealing all the problems, like how nice am I? And anyways, so let's do just one graphing problem, which is on the next page. 5x over x minus 1. Sketch the rough graph. Okay, so here apparently like this is not the multiple choice, so we have to do it by hand. Okay, so now let's find all of the asymptotes. So the vertical asymptote. Okay, so first you can easily verify that you cannot factor top or bottom, so there's no common factor obviously. So for the vertical asymptote, what do? You set bottom equal to 0, so x is equal to 1. Okay, and then horizontal asymptote. So that means you look at the degrees, the top degree and the bottom degrees. Now both are equal to what? 1, right? Okay, so they're the same. So what does that mean? You look at the leading coefficients. Okay, you look at the leading coefficients. What are the leading coefficients? 5 and 1, right? Okay, so the horizontal asymptote is at y equals 5 over 1, which means y equals 5, right? Okay, and what about the oblique asymptote? Is there one? No, right? Okay, so there is no oblique asymptote. Okay, and now let's find the y-intercept. So what do you do here? Set x to 0, right? Okay, so now when you set x to 0, what do you get? 0 over negative 1. And 0 over negative 1 is what? Undefined 0 or negative 1.
0.
0, right? Yes. Okay, so the y-intercept is at 0, 0. Okay, so now x-intercept. So now for the x-intercept, you said y equal to 0, right? And what does that mean? That entire fraction, 5x over x minus 1 is equal to 0. Okay, so now ask yourself, fraction is equal to 0, so what does that mean? What has to be equal to 0? Top or the bottom? When the bottom is equal to 0, what do you have? Undefined, right? So what does that mean? This implies top has to be equal to 0. So that means what? X is equal to 0, right? Okay, so it has the same x-intercept as the y-intercept. Okay, so now let's find a few other points. So here we'll see about 3 additional points. So here is a table of x and y values. Okay, so now let's choose some negative values and some positive values. So how about x is equal to negative 2? Okay, and then negative 1. Now, you can plug in 0, but what do you expect to happen? 0, right? Okay, so 0 is meaningless. So now, you can try 1, but what's the problem here? When x is equal to 1, you have 0 denominator, right? And we already got that x equals 1 is the vertical asymptote. Okay, so you cannot put 1, so you have to put 2. Okay, and maybe one more, 3. Okay, so now when x is equal to negative 2, what's the value of y? Negative 10 over negative 3, right? And what does that mean? It's positive 10^3, right? Which cannot be reduced. And when x is equal to negative 1, you have negative 5 over negative 1 minus 1, so that's negative 2. And so you just have positive 5 over 2, right? Okay, and when x is equal to 2, you have 10 over 1, which is equal to 10. When x is equal to 3, you have 15 over 2. Now here we got like 3 fractions. But remember, I'm just like trying to get the graph, like not that I'm doing the homework, like graphing this by hand on homework, so fractions are fine. Okay, so now let's sketch the graph. Okay, so now first, it has vertical asymptote at x equals 1. And remember, vertical asymptote means what? The graph blows up or falls down, right? Around this line. And it has x equals 1, so where is it? Maybe somewhere here, right? Okay, and now it has horizontal asymptote at y equals 5. So what does that mean? So 1, 2, 3, 4, 5. So that is the horizontal asymptote, right? Which means what? The graph will start to resemble a horizontal line, right? Okay, and then a few points. 0, 0, x-intercept and y-intercept. And then -2, comma 10/3. So -2, 10/3. Now 10/3 is what? A little over 3, right? So what does that mean? Here is 3. So maybe it will have somewhere here. And then -1, comma 5/2. So 5/2 is what? 2.5, right? So that will be somewhere here. And then 2, comma 10, so that's like way up there. And then 3, comma 15/2. 15/2 is what? 7.5, right? So that means maybe somewhere here. Okay, so now based on how these points are lined up, can you see the shape of the graph? So remember, any rational function will have this kind of shape, right, as the graph, or maybe the other way, like this. But do you see the curves here based on how the points are lined up? Where's the first curve? This one, right? Okay, and where is the second curve? That, right? Okay, so the graph has to resemble a horizontal line around this dotted line, and the graph has to blow up or fall down around this horizontal or this vertical line, which is the case. Okay, but keep in mind that you may see these two curves as well, like which is on the second and fourth quadrant. Okay. Okay, so that's the end of 3.5, and now let's go to section 4.2. Okay, so we already did 4.1 as part of exam 2, I believe. Okay, so 4.2 is about exponential functions. Okay, so all of you have seen exponents before. What does exponential function mean? So any exponential function can have these two forms. Number one, f of x is equal to a to the power x. Okay, so what do you notice? X is in the exponent. Okay, now this is the exponent. What is the name of this a? Like, how do we call it, basically? No idea? Yeah, so usually people have kind of trouble identifying this name. So here is the first syllable, B. Does it remind you anything? No? Okay. Here's the second syllable.
Base.
Base, yes. Okay, so now what is the condition on this base? It's positive other than 1. And now, hopefully you can see why. What happens when the base is equal to 1? You have 1 to the power x, right? And what is 1 to the any power? 1, right? Which is not an exponential function, so that's why we exclude in this case. And now the second form, which is a bit less normal, is this, b times a to the power x. Now here, what do we do first? B times a or a to the power x? According to PEMDAS, we do exponents first, right? Instead of multiplication. So this means this, but you may not see the parentheses. Okay, so once again, any exponents has x in the exponent. Okay, so now let's work on the two basic problems. Graph f of x, which is equal to 2 to the power x. Okay, so once again, it's not 2 times x, it's 2 to the power x. And here, we will be a little bit inefficient and traditional at the same time, which means, let's fill in the blanks. Okay, and I will choose specific x values. -2, -1, 0, 1, and 2. Okay, so now here to fill in the blanks for y, we will go backwards. Okay, so start from 2. What's the value of y when x is equal to 2?
4.
4, yes, do you see that? 2 square, right? And when x is 1, what's the value of y?
2.
2, right? 2 to the first power. And now, when x is equal to 0, what's the value of y? 2 to the power 0, right? What is 2 to the power 0? Zero. Now, am I correct or no? 2 to the power 0 is 0. Yes or no? Yes? No. What is anything to the power 0 equal to?
Itself.
1, yes. Okay, so many people say 0 for this, which is why I put a star here. Okay, be careful. Anything to the power 0 is 1, not 0. And now, here is another tricky part. When x is -1, y is 2 to the power -1, right? Okay, that's obvious. But where is 2 to the power -1? -2? which seems to be the case, right? What is 2 to the power negative 1? And notice that I'm not using my calculator here, because if similar problems like this appear on your final, where it's non-calculator final throughout all problems, you must know how to find them by hand. What is 2 to the power negative 1 equal to? Again, it's not negative 2, although that seems to be the case. And hopefully you remember this rule from the exponents. So what is 2 to the power negative 1 equal to? 1 over 2 to the first power, right? Which is equal to 1/2. Okay, now this is not the developmental class, so I cannot go over the rules of exponents. If you forgot, Google rules of exponents. You'll see millions of pages or websites that has rules of exponents. So please review, okay? I cannot review it here. And now, when x is equal to negative 2, you have y is equal to 2 to the power negative 2, which is not equal to negative 4. And what's that equal to?
1/4.
1/4, yes. Okay, again, it's because 1 over 2 squared. Okay, so now, how does the graph look like? So here is xy plane. So now, negative 2, 1/4. So here's negative 2. And then, so here's 1, and 1/4 will be maybe somewhere here. And then negative 1, 1/2 will be somewhere here. 0, 1 is here. And then 1, 2 is here. And then 2, 4 is up here. Okay, so now based on how these 5 points are lined up, they are not part of the line, right? Rather, it is a curve. And the curve looks like this. Okay, so that's the graph of 2 to the power x. And now part B, or number 2, 1/2 to the power x. And we'll do the same thing here. So first we will choose the same x values. Negative 2, negative 1, 0, 1, and 2. Okay, so now, again, we will go backwards. When x is equal to 2, we have 1/2 to the power 2. And what's that equal to?
1/4.
1/4, right? Yes. Because it's 1/2 times itself. And we have 1/2 to the first power when x is equal to 1. And anything to the first power is equal to itself. So it's just 1/2. And now, when x is equal to 0, what's the value of y? 0? No, it's equal to what? 1, right? Okay, once again, anything to the power of 0 is not 0, it's equal to 1, right? And now, here comes the tricky part. When x is equal to negative 1, we have 1/2 to the power negative 1. And what is that equal to?
2.
2, yes. Do you see why? Because there is this rule, hopefully you have seen this before. So what does it mean? Whenever you have fraction to the negative power, you can drop the negative sign, but you have to flip the fraction inside. So what does it mean? This one means 2 over 1 to the first power, which is equal to 2, right? Yes. And when x is equal to negative 2, you have 1/2 to the power negative 2, and what's that equal to? 4, right? Yes. Okay. Again, the reason is it's 2 over 1 to the positive second power, which is 2 squared, which is equal to 4. Okay, so now, how does the graph look like this time? So here's negative 2, and then 1, 2, 3, 4. So it passes this point, and then negative 1, comma 2 is here, and then 0, comma 1, and then 1.5, so that means here, and then 2.25, so that's somewhere here. Okay, so the graph is again not a line, but the graph looks something like this. Okay, so now let's go back to the first example, which was 2 to the power x. Here, what is the base? 2, right? Yes, so the base is equal to 2. Okay, so now for 1/2 to the power x, notice that we can rewrite this as 1 to the x over 2 to the x by distributing x, and 1 to any power is 1, so we have 1 over 2 to the power x, which can be rewritten as 2 to the power negative x. Now, does that mean 2 is the base? No. Okay, that is not the base. And what's the reason? That negative sign. Okay, if you look at the basic exponential function, it has a to the positive x, okay, not a to the power negative x. So here, what is the base? This is not the base. What's the base? 1/2. Okay, so it is essential to correctly identify the base. Why? Because you must have a positive sign x in the exponent. Okay, positive sign. If you have negative sign x, just like here, 2 to the power negative x, that 2 is not the base. Okay, so you must have just x in the exponent so that you can identify the base. Now, the good news is we got this kind of increasing curve and we got the decreasing curve for the second problem. These two are the only basic graphs for exponential functions. Okay, so let's look at several characteristics for these two exponential graphs on the next page. Okay, so here are the facts about a to the power x. Now, remember the condition for the base was positive other than 1. Okay, so that's why we have these two subcases. Number 1, a is greater than 1. For example, f of x equals 2 to the power x. Okay, so how did the graph look like? It was an increasing curve, right? And it will have the exact same graph. This. Okay. And now, is there any y-intercept? Yeah, it's right here, right? And what do? You set x to 0, So what do you get? A to the power 0, but remember anything to the power 0 is 1, right? So the y-intercept is at 0, 1. And now, does it have x-intercept? It seems like it does, right? Especially where? Here. Okay, but the fact is there is no x-intercept. Now, the graph gets closer to the x-axis, and then it starts to resemble the horizontal line. Have we seen this phenomenon before? Yeah, like in today's class, right? What does that mean? This is the horizontal asymptote, right? Okay, so where is the horizontal asymptote? Y equals 0, right? The x-axis. And now, does it have any vertical asymptote? In other words, is there any like imaginary dotted line in the middle of the graph so that the graph blows up? Is there one? No. Okay, now this is the portion that the graph is blowing up, but it does not approach any vertical dotted line, right? It just keeps increasing like that. Okay, so the vertical asymptote, there isn't one. What about the oblique asymptote? Is there one? No. Okay, and now, as obvious from the graph, it's an increasing function. Why? Because the graph is going up. Okay, and now, by just looking at the graph, what seems to be the domain of this function?
Everything.
Everything, yes. And now, what seems to be the range of this function by just looking at the graph?
Everything greater than 0.
Greater than 0, yes. Which means what? 0 to infinity. And here, we do not put the bracket around 0 because we saw that the graph does not touch the x-axis. And there's no graph below x-axis, so any negative values is not the range, right? Okay, so now we did the hard part. Case number 2, a is less than 1. So what does that mean? Like f of x equals 1/2 to the power x, which is the example number 2. And now there, how did the graph look like? This decreasing curve, right? Okay, so same thing. The graph will have the decreasing curve. Okay, and then everything else stays the same as the previous case. Well, actually, hopefully you can realize that this is my lie. I've told you a lie. Now, why? Because it's not everything stays the same. It's almost everything except what? This one. Okay, so this one is kind of false, almost. Okay, so it's almost because this is a decreasing function, right? Okay, and then everything else stays the same, yes. Okay, so other than this kind of trivial fact, which is a decreasing function, everything else stays the same. Okay, so now we have looked at all the basics of the exponential functions and their graphs. And now here's a special case. And now the calculator comes in. Finally, for the first time in like a million years, another calculator comes in. Woo, what a relief, right? So now, hopefully you have your calculator ready. Okay, so let me grab my calculators. So I don't know what kind of calculator you have, but if you have this calculator, which is the graphing calculator, so this is TI-84, and remember I said the price for this is kind of over $100. Yeah, it's not the price I said, so don't put any complaints on me. I'm not the guilty one. And if you have this calculator, so this one is a scientific calculator, which means non-graphing calculator. Okay, so this is a whole lot cheaper than the graphing calculator, but no matter which calculator you have, so on your calculator, find the ln button. Okay, ln. Okay, so let's see. If you have this graphing calculator, ln is right next to the number 4. Okay, but if you have this calculator, ln will be the third button from the top. Okay, so now right above this, you'll see this e to the power x. Do you see that? Like here you have e to the power x right there. And then also here you have e to the power x, this like blueprint. Okay, now what does that e represent? So e is not the 5th syllable in the alphabet. I mean, it is the case, but not in math. E means the natural number. That's just the name. Now, how do you look at this e? Okay, so first of all, you have to turn on your calculator. That's obvious, duh. Okay, and then you have to type second ln. Okay, so turn on your calculator, obviously, and then press second ln. Okay, so now here I cannot adjust the light, but so press second, which is this one. Okay, second, and then ln. Okay, then you see e to the blink. Okay, so you just put 1, and then you type 1. Okay, and then hit enter, of course. Okay, so what do you get? 1 and then enter. So you get this 2.718281828. And if you see that, you are seeing the right thing. And now, this is a long decimal, but the problem is this is not the ending decimal. The digits never end. Okay, so e is approximately equal to 2.718, but e is not equal to 2.718. E is just e. Okay, so e is an unending decimal. Okay, e is not 2.71 or 2.7 or 2.72. E goes forever. Okay, now when this e becomes the base of the exponential function, we say it's the natural exponential function. Why? Because the base is the natural number. Okay, and now how does its graph look like? So the graph is either this increasing curve or the decreasing curve. And remember, the threshold is what? At 1, right? If it's greater than 1, we have an increasing curve. If it's less than 1, we have a decreasing curve. Do we have an increasing curve or the decreasing curve here? If the base is equal to e. What will be the case? Increasing. Do you see why? Because the base is what? Greater than 1, right? I mean, e is over 2, right? So your e is certainly greater than 1. Okay, so that's why we have an increasing curve. Okay, so now let's look at a few problems. on the next page. Okay, so now put the calculators away for now. So f of x is equal to 3 to the power x. Find each. So part A, f of -2. Okay, so that means we plug in -2 to x, so we get 3 to the power -2, right? And now 3 to the power -2. Is that equal to -6? -9? No. What's that equal to?
One-third.
1/9, right? Okay, because it's 1/3 squared, which is equal to 1/9. And now f of 3/2. So this means 3 to the power 3/2, right? Okay, so now we covered this in, I think, chapter 1, but there is a way to convert this into radical expression, some kind of root, basically. Hopefully you remember this. Now, what kind of root do we have? Cube root or square root?
Square.
Square root, yes. And what goes under the square root symbol? Which number?
Three. Or
I guess I can write that as a hint. What goes under the square root symbol? 3
three.
cubed. Remember that? Okay, so that number goes here and that number goes to the inside power. Okay, so this means what? Square root of 27, right? Now, are we done? No. Okay, why not? Because you can do something on this one, which is what? Simplify, right? Okay, so what is this? 9 and 3, 3 and 3. So what do you get? 3 square root of 3, right? Okay, notice that I'm not using calculator here. I could, but I'm not. Okay, because again, see, if similar problems appear not only on exam 4, but also on the final, you have to know how to evaluate this by hand. Okay, and the reason I'm not using it is because I have to pretend that I have, or as if I was you, I would have to know how to do this by hand. Okay, not because I don't want to do it. Okay, sure, calculator is really convenient, but sometimes that cannot help us. Now, number 2. So 1/4 to the power -x. Find each. F of 2. So this means 1/4 to the power -2, right? And now, what is 1/4 to the power -2 equal to? -16? -8?
Positive 8.
+16. Do you see why? So you drop the negative sign and then you flip the fraction, right? So you have 4 squared, which is equal to 16. Okay, and now f of -3. So this means 1/4 to the power. Now, what is the exponent here? -3 or +3? positive 3, right? Okay, and now what is 1/4 to the power positive 3 equal to? It's 1/4 times 1/4 times 1/4, right? What's that equal to?
One over 64.
1 over 64, yes. Okay, and now graph of f of x. Okay, so we know it's either this or that. Is the base equal to 1/4 here? No. And what's the reason? Because that, right? Okay, so 1/4 is not the base, so the graph shouldn't be the decreasing curve. Then what is it? So remember, f of x was 1/4 to the power negative x, but if you drop the negative sign, you have to flip the fraction, so you have 4 over 1 to the power positive x, but that's precisely equal to 4 to the power x, and so that is the base, right, which is greater than 1. Okay, so what does that mean? The graph will be this. Okay, be careful. Before you check whether you have negative x or positive x, you cannot identify the base, okay? So you must check for the negative sign or positive sign exponent in x, and then you can identify the base. If you have negative x, then you have to rewrite so that you have positive x in the exponent. Okay? So, any questions over these problems? Now, let's do 2 graphing problems. So, graph 2 to the x minus 4. Okay, so now here, we will do these graphing problems in a different way. Okay, so first, how do you get the graph of this from the parent function 2 to the x? So you subtract something in the back, right? Does it remind you anything in terms of like transformation or translation stuff?
Goes down 4.
Right, go down 4. Remember that? Okay, so this means move 2 to the x down 4. Oops, down 4. So now, instead of choosing several points for 2 to the x minus 4, let's choose several points for 2 to the x. Okay, so now, what do we have here? So now, earlier we chose like -2, -1, 0, 1, and 2. But to avoid any fractions where we got the fractions for x being equal to -2 and -1, I'll just choose, actually, maybe that. So these 4 numbers, 0, 1, 2, and 3. Okay, so now when x is equal to 0, you have 2 to the power 0, that's equal to 1, right? When x is equal to 1, 2 to the first power, so that's 2. When x is 2, you have 4. And when x is equal to 3, you have 2 cubed, and that's 8, right? Okay, not 6, right? Okay, so now, why did we choose several points for 2 to the power x? Because now can you apply this? down 4 to these 4 points. Okay, so in other words, down 4 to these points. So what does that mean? First, 0, 1. When you go down 4, where are you? 0, negative 3. Do you see that? Because what do? You subtract 4, right? From 1. And then 1, 2. You go down 4, so where are you? One comma, and then 2 minus 4, right? So it's negative 2, yeah. And then 2, 4, and then you go down 4, so you are at 2, 0, right? And then the last one, 3, 8, so that means you are at 3, 4, right? Okay, so how does the graph look like? So the graph looks like, so 0, negative 3, so that's here. And then 1, negative 2, so that's here. And then 2, 0 is here. And then 3, 4 will be way up there, right? Okay, so you can kind of guess that that is the curve, right? I mean, like roughly, okay? Okay, and this graph is the graph that's being shifted, you know, down 3, right? Okay, I mean, like the graphs don't quite match, but, you know, like I'm just like horrible artist, so there we go. Okay, so that's the graph, and then part B, 2 to the power x minus 4. Okay, so now here we'll do the same thing. Now, does this mean we move 2 to the x down 4? No. Where do we go?
Right 4.
The right 4, yes, right? Okay, right 4. So this time we move right 4. And now, let me legally steal these 4, or yeah, these 4 points, okay? Yeah, that's called the legal burglary. Okay, because we'll just use the same exact 4 points. And now, what do we do? You apply right 4 to these 4 points. Okay, so first, 0, 1. When you go right 4, that means what? You have to add 4, right? Add 4 to where? 0 or 1? 0, right? So what do you get? 4, 1. Okay, and then 1, 2. When you add 4 to 1, what do you get? 5, 2, right? Okay, and then 2, 4. So when you add 4 to 2, you get 6, 4. Okay, and then lastly, 3, 8 becomes what? 7, 8, right? Okay, so now, sketch the graph. So sketch the graph. So 4, 1. So 1, 2, 3, 4, 1. That's here. And then 5, 2. So that's here. 6, 4. Here. And then 7, 8. 5, 6, 7, 8. Maybe somewhere here. So how does the graph look like? The graph looks something like this, right? Okay, so notice that this graph is kind of similar to the original graph, which is this one, right? But what's the difference? What's the difference? This one is shifted to the right 4, right? So this kind of like flat-ish portion happens all the way until like what? When x is equal to 2 or 3, right? And then this uphill slope does not start until like x is equal to 4. Okay, so that's the only difference. Okay, so any questions on these graphings? Okay, so now let's briefly start the next concept, which is basic exponential equations. Okay, so now we will see not so basic equations in section 4.5, but here we will be dealing with very basic equations. And basic exponential equations mean the bases are related. Okay, so now that is such a vague word, related. And you will see what I mean by this once we do the problems. Okay, so at this point, related is not that clear, but you'll see what I mean by this. Now, here is the scheme of solving such basic exponential equations. To solve them, first, make the bases the same. Make bases equal to each other. And then, okay, so here the keyword is and then. So once you have the same basis, you set exponents to be the same as well. Okay, so first you need to have the same basis, and then you can set exponents equal to each other. Okay, so now maybe let's do 1 or 2 problems here just to illustrate what I mean by this. Okay, so number 3, 27 to the power x is equal to 3. Okay, so again here, please don't do divide by 27. Okay, that's just like way wrong, right? Okay, so don't do divide by 27. So here, there are 2 numbers. And what are they? 27 and 3, right? Are they related? Okay, yeah, 27 is 3 times 9, but not in terms of multiplication. So is 27 and 3 related? And how are they related? 27 is equal to what in terms of 3? Again, don't say 3 times 9. Use exponential form. 27 is equal to what? 3 cubed, yes. Okay, so we have 3 cubed to the x is equal to 3. Okay, so now step number 2, clear parentheses. Okay, so how can you clear parentheses here? 3 cubed to the power x. When you have so-called double exponents, what can you do? Multiply the exponents, remember that? Okay, so you have 3 to the power 3x is equal to 3. And now here, do we have the same basis? Yes, and what is the same base? 3. Okay, so these are the same bases. Okay, now, once we have the same basis, what can we do? Set exponents equal to each other, right? Now, what are the exponents? 3x, that's obvious. But what is this exponent equal to?
Is it 1?
1, yes. Okay, it's invisible exponent, but it doesn't mean it's not there, right? It's 1, yes. Okay, so 3x is equal to 1. So x is equal to 1/3. Okay. So tomorrow we will see a few other fancy looking problems. So this is the most basic exponential equation. Okay, so first we need the same basis and then we'll set exponents equal to each other. Okay, so tomorrow what we will do is we will finish off these kind of big number 3, okay, which has like multiple parts, and then we will look at a few word problems and then we'll go from there. Okay, so even though we couldn't finish 4.2, which was expected, obviously, I don't think taking exam 4 on Thursday will cause any problems, so let me stick to that. But if we indeed fall behind after tomorrow's class, then I guess we can just move the exam 4 to Friday, but I don't want to do that. So we'll see how it goes, okay? So if you have any questions, just feel free to stay until like 12:30 and ask any questions. If not, have a good afternoon. I'll see you tomorrow at 10.